Someone or something is calling us from interstellar space. Could it be aliens? Or could it be something far stranger?
Something striking just happened to Voyager 2.
Science team, that was a unique experience which will be the highlight for many of the careers of the Voyager scientists.
For more than 46 years, this interstellar object has been sailing through space, firing off routine signals. But now, strange fluctuation has emerged in the plasma wave data, and it is pulsing with a kind of precision that caught NASA off guard.
It came from another star, glowing, shifting, and now silent. NASA has the images, but the agency is silent for now.
When scientists compared these readings to earlier anomalies found in Voyager One's telemetry, they discovered that this object didn't just appear out of nowhere. It may have been following Voyager 2 for a very long time. The anomaly NASA couldn't explain. On July 21st, 2023, NASA lost contact with Voyager 2.
NASA has lost contact with one of its longest-serving space probes. Transmission has gone dark from Voyager 2.
This was right after the spacecraft received a misdirected command that adjusted its antenna orientation by about 2 degrees. This pointed it slightly away from Earth and cutting off its ability to send and receive data. While this might seem like a minor deviation, at a distance of over 19 billion kilometers from Earth, even the smallest misalignment is enough to sever communication entirely. Over the next 2 weeks, engineers at NASA's Jet Propulsion Laboratory worked to recover contact, and on August 4th, the Deep Space Network successfully detected a carrier signal from the spacecraft. They transmitted a correction command using the Canberra facility's 70-meter dish. By August 6th, Voyager 2 resumed transmitting engineering and science data. While the initial relief was focused on regaining contact, analysis of the returned data revealed something that did not align with expectations.
Well, there's hope that NASA could regain control of the lost Voyager 2 probe after a heartbeat signal was picked up.
The plasma wave subsystem showed repeated voltage fluctuations that, when charted over time, formed a stable pattern. These pulses were not random and did not correspond with background solar activity, making natural interference or noise an unlikely cause. Engineers ruled out internal malfunction after confirming the instrument's health and stability. The consistency of the signal pattern reduced the probability of a cosmic ray event or sensor error. The simulations confirmed that cosmic rays would produce highly erratic signals. This meant it would not result in the type of regular waveform Voyager 2 was transmitting.
NASA was able to confirm that Voyager 2 is still broadcasting. It's hoped that a scheduled reset of the probe's systems in mid-October will allow communication to be re-established.
Shortly after these anomalies were observed, mission navigators noticed a slight deviation in Voyager 2's trajectory. The probe had always maintained a consistent, predictable outbound course. But now, its motion showed a gradual curve that did not align with the expected path modeled using gravitational influences alone. The probe was still moving outward into interstellar space, but the updated trajectory introduced a lateral component. This could not be explained by natural sources. What raised concern was the timing. The trajectory shift coincided closely with the start of the plasma pulse pattern. That correlation introduced a new problem, that Voyager 2 appeared to be reacting to something external. The course change was extremely subtle and would not have been detectable if not for the precision of long-term tracking, but it was real. Further analysis also showed variations in data from the magnetometer, one of the spacecraft's original instruments used to measure magnetic field strength and direction. The recorded spikes in magnetic field intensity occurred within the same window of time as the plasma wave pulses and mirrored the same rhythmic pattern. The field strength did not align with known interactions with charged particles or solar remnants. NASA has previously encountered plasma and magnetic field anomalies during both Voyager missions, especially during their crossings of the heliopause.
It's been 4 decades of a long journey, but now the Voyager 2 spacecraft has finally bid farewell to our solar system.
However, those events were chaotic and explained by shock waves from the solar wind interacting with interstellar space. What Voyager 2 showed in mid-2023 was neither chaotic nor easily attributable to known space physics. While engineers considered the possibility of an ionized gas cloud, that explanation soon fell short. The stability of the signal and the fact that gas clouds of that density and uniformity are rarely found at that distance from the Sun. Similarly, the micrometeoroid cluster hypothesis did not align with the long-term consistency of the data. In September, NASA began coordinating with additional observatories to confirm whether any similar patterns could be detected from Earth. These observatories were capable of performing narrow-band scans at the frequencies used by Voyager 2. A low-frequency signal matching the pulse pattern from Voyager 2 was eventually logged by a telescope in the Atacama region. The detection occurred nearly 2 weeks after the original pulse event. It was consistent with the expected delay caused by the vast distance between the probe and Earth. The waveform had degraded slightly by the time it reached the ground-based receivers, but the pattern was still identifiable and distinguishable from background radiation. NASA has not made a public announcement directly linking the pattern to an external presence. However, internal documentation reportedly reclassified the plasma data as a tracking anomaly. At this stage, all available data points to 3 consistent observations: a persistent plasma wave signal with repeating structure, a corresponding shift in trajectory that deviates from gravitational expectations, and magnetic field readings that appear to pulse in sync with the plasma activity. If this influence continues, and if the external signal maintains its proximity, then Voyager 2 may not be moving alone through interstellar space. It may be moving in conjunction with something else. And while that presence has yet to reveal itself in any visible or detectable form, its influence is now part of the official telemetry record, a pattern in the dark. After the irregularities in plasma data and trajectory were flagged, Voyager 2's tracking logs were reviewed in detail. What emerged from that analysis was a link between the timing of the signals and adjustments in the spacecraft's velocity vector. Each time the plasma wave instrument recorded a burst of activity, the flight path data showed a tiny deviation from the predicted trajectory. These deviations did not resemble a course correction or emergency maneuver, but the probe's trajectory, which had been modeled with extreme precision, no longer matched expectations. Voyager 2 is not equipped with onboard propulsion that could account for changes in direction. Its movement through space is entirely determined by gravitational dynamics and initial launch velocity. Any deviation from its expected course must be attributed to external forces. The projected location of this unseen influence was calculated to be within approximately 300,000 kilometers of Voyager 2, roughly the same distance between Earth and the Moon. In interstellar terms, that is extremely close. At that distance, an object could easily remain outside the view of all current ground-based telescopes if it did not emit visible light or infrared radiation. The L object did not drift randomly past the spacecraft or interfere intermittently. It appeared to be pacing with it. It was maintaining a relatively constant distance and direction. The pattern here suggested active control, or at least some form of inertial regulation. Engineers and scientists reviewed Doppler tracking data to determine whether the probe's signal was being affected by reflection or absorption. In one of the cross-checks, a faint signal delay was observed, inconsistent with Voyager's known location and position. The delay was small, measured in milliseconds, but repeatable. When these delays were plotted over time, they formed a consistent curve that corresponded with the periods during which the plasma wave anomalies occurred. The signal behavior of this object is rare, but not unprecedented. Echoes can occur when a spacecraft signal bounces off a nearby body and travels a longer path back to Earth. However, for such an echo to be present, there would have to be a reflective surface in close proximity. That surface would need to remain at a fixed offset for the echo timing to be so stable. The idea of a nearby reflective object was not ruled out. However, no corresponding visual or thermal data supported its presence, and the signal's regularity made it unlikely to be caused by a dust cloud or disintegrating fragment. Those would typically scatter the signal in unpredictable ways. At this point, researchers revisited earlier mission data, anomalies in Voyager 1's long-range trajectory, to compare. A previously dismissed delay in Voyager 1's telemetry, logged in the early 2000s, now showed similarities to the delay patterns being observed in Voyager 2's signal path. The waveform curvature, when overlaid with recent telemetry, aligned closely enough to suggest a shared underlying cause. If both probes experienced similar distortions in signal propagation and course modeling, and if those distortions followed the same rhythmic sequence, then there is a basis to explore the theory that both Voyager missions were affected by the same external influence at 2 different points in time. Signals beyond noise. After the unusual plasma wave activity and course deviations were logged, engineers turned their attention to the raw carrier signal transmitted by Voyager 2. Every communication from the spacecraft includes a base signal, which carries not only the science and engineering data, but also embedded characteristics that reflect the probe's environment and signal path. While the spacecraft's encoded data packets appeared intact, what drew attention was the structure of the noise within the signal's lowest detectable levels. Across several consecutive transmissions, a pattern emerged in the baseband carrier that was not seen in earlier mission data. The anomaly consisted of a recurring peak within the noise floor, showing up as a faint but structured step-like waveform that appeared at regular intervals. Engineers examined the waveform and ruled out onboard signal processing errors, as Voyager 2's communication systems had remained stable with no signs of degradation or interference. A Fourier transform of the waveform, a method used to identify repeating frequencies hidden inside complex signals, revealed a narrow set of harmonics that were evenly spaced. In standard conditions, signal noise in deep space telemetry is irregular and reflects background cosmic microwave activity or system static. Structured harmonics, by contrast, typically arise from engineered systems or repeated environmental interference. The engineers found no evidence that the pulses matched any known space weather event, such as solar flare activity or plasma turbulence from the heliosphere. Nor did they match echoes caused by ground-based electronics or atmospheric distortion. The harmonics remained stable across multiple ground stations receiving the signal, including Canberra, Madrid, and Goldstone. This consistency eliminated the possibility that the anomaly originated on Earth. The signal anomaly was not limited to one session. Over the span of 3 weeks, engineers documented at least 6 distinct downlink sessions in which the same harmonic structure was observed. Each occurrence showed a 3-part pulse followed by a short pause, and then a single, stronger peak. The cycle repeated every 7 seconds, a detail that remained consistent regardless of the ground station or time of day. Although the signal strength was faint, its stability raised the question of whether Voyager 2 was receiving and retransmitting something that was not part of its own onboard systems. A possible explanation considered by mission scientists was that an external signal source was interfering with the spacecraft's carrier frequency through either reflection or close-range electromagnetic interaction. Another theory suggested the spacecraft was unintentionally serving as a passive relay for a signal that had entered its immediate environment. In an effort to rule out local equipment issues, NASA involved independent radio observatories capable of narrowband scanning in the X and S band ranges. Observatories in South Africa, Chile, and Japan confirmed that they had also detected a signal with the same 7-second rhythm. Though weaker and more difficult to isolate from background noise, the waveform's harmonic structure matched what had been observed in the Voyager 2 carrier signal. The fact that different observatories on different continents detected a nearly identical pulse pattern indicated the signal was not an artifact of one set of instruments or conditions. This raised the possibility that a low-frequency emission was present in the interstellar medium and that Voyager 2 was situated within the path of that emission. In response, a team of radio astronomers used a machine learning model trained on over 20 years of deep space signal data to classify the waveform. The model was designed to distinguish natural astrophysical signals such as pulsars, fast radio bursts, and planetary radio emissions. The Voyager pulse pattern did not align with any known examples in the dataset. The signal was determined to be non-chaotic, meaning it had a predictable structure that repeated with minimal deviation. In signal analysis, chaotic systems are associated with natural environments, while non-chaotic signals typically come from stable transmitters or systems designed to maintain phase coherence. The 7-second repetition interval and phase stability across multiple detection sites eliminated the possibility of a transient noise artifact. To further validate the finding, researchers compared the Voyager 2 signal to historic signal artifacts, including the so-called WOW signal detected in 1977. The Voyager signal lacked the spike intensity of that one-time detection, but was more structured in form and longer in duration. Engineers also modeled the signal delay variation based on Earth's orbital position relative to Voyager 2. When Earth was located on the far side of the Sun, the pulse timing shifted by a fraction of a second, consistent with the expected time delay effect due to light travel distance. However, there was an additional phase alignment adjustment that suggested the signal source might be reacting to the change in position, rather than simply reflecting a fixed origin. If the emission were originating from a passive body, such as a fragment of ice or a dust cloud, its behavior would not account for this alignment. If instead the signal was being produced by a coherent source located near Voyager 2 and adjusting in sync with the Earth's position, then it could imply either an intelligent response or an automated beacon with positional awareness. No claim has been made by NASA or collaborating observatories that the signal represents a form of communication. However, the structured repetition, consistent phase, and distance-based modulation effects strongly suggest an origin that is not chaotic and not explained by current models of the interstellar environment. While the presence of electromagnetic patterns in deep space is not unusual, their behavior is typically governed by random variation, interference, and entropy. The signal from Voyager 2's carrier stream does not follow that pattern. It shows signs of design, or at minimum, consistent generation from a single stable origin, and it has not disappeared. It remains active in periodic bursts, still synchronized to the spacecraft's known coordinates and velocity vector. If there is an origin point near Voyager 2, then either that source is moving with the probe, or the signal is being projected in a narrow beam that remains focused on its position. In both cases, the behavior is difficult to attribute to a natural body or debris field. What this suggests is not proof of intention, but evidence that something with signal-emitting capability may be operating in close proximity to the probe, and that signal has now been independently detected from Earth. A 40-year echo. After the detection of the anomalies in Voyager 2's data, mission analysts turned their attention to archival telemetry from Voyager One. It had been launched 16 days earlier in 1977, and is currently the most distant spacecraft ever built by humans. Although the two probes took slightly different paths after their planetary flybys, their onboard instruments and communication systems were nearly identical, and comparisons between their deep space data have long been part of standard mission analysis. Voyager 1 crossed the heliopause and entered interstellar space in 2012. Since then, it has continued to return low-bandwidth science data, though at a slower rate due to its greater distance and reduced power reserves. While its trajectory has remained stable, engineers reviewing its historical signal logs identified multiple instances of irregular telemetry timing and signal distortion that were previously considered either benign or unexplained. One of the most notable cases occurred in 1996, when a phase shift was detected in Voyager 1's signal carrier. A phase shift refers to a change in the waveform alignment of the signal without a change in frequency or amplitude. This type of distortion typically indicates interference or propagation anomalies. The shift in Voyager 1's case lasted for approximately 7 seconds and then resolved without affecting the main data payload. It was logged as a transient anomaly and received no follow-up investigation at the time. After the 7-second rhythm in Voyager 2's recent signal pulses became evident, the older Voyager 1 phase shift gained renewed attention. When the waveform was plotted against Voyager 2's current signal structure, the timing and shape aligned closely. The similarity was sufficient to suggest that the same external cause might have been involved in both cases. In addition to the 1996 phase event, analysts reviewed telemetry records from the early 2000s and found several entries. There were small but repeated communication delays. These delays, ranging from a few milliseconds to just under 1 second, did not correspond with orbital changes caused by Earth's movement. What changed in the recent analysis was the application of pattern recognition software used to model Voyager 2's anomalies. When the Voyager 1 signal delays were run through the same algorithms, they displayed a near-identical rhythmic curve to the signal anomalies found in Voyager 2's more recent transmissions. The repetition intervals, delay durations, and harmonic structures were consistent enough to indicate a shared influence. Examination of magnetometer readings from Voyager 1 during its heliopause crossing showed irregularities in the local interstellar magnetic field, including unexpected field strength drops that did not align with solar modeling at the time. These were not investigated in detail, partly because they occurred outside the window of greatest interest during the boundary crossing. In hindsight, the data suggests that Voyager 1 may have encountered a region of space with properties similar to those now surrounding Voyager 2. A key discovery came from archived analog telemetry tapes stored at the Jet Propulsion Laboratory. In 1983, a corrupted signal segment had been captured during a high-gain antenna calibration sweep following the Saturn flyby. The segment was preserved but never decoded due to its poor quality and lack of identifiable data framing. With modern digital tools, the waveform was reconstructed, revealing a low-amplitude signal segment that included repeating peaks spaced evenly across a 7-second interval. This early signal, although degraded, resembled the pulse structure currently observed in Voyager 2's carrier noise. The existence of such a pattern, dating back over 40 years, adds weight to the theory that the same environmental influence may have affected both probes at different times. If this is the case, it implies that the phenomenon in question is not localized to a fixed point in space. Instead, it may be mobile, distributed across a broader region, or capable of persisting over time while interacting selectively with spacecraft traveling in specific trajectories. The possibility that both Voyager probes have encountered the same influence decades apart and at vast distances from each other raises questions about the scale and consistency of the source. Neither spacecraft has the ability to change its course or respond to external forces beyond passive movement, so any persistent interaction must be the result of the probe moving through a region where this influence already exists. Whether this is a naturally occurring electromagnetic structure, a long-range gravitational effect, or something artificially generated is still unknown. The fact that both probes responded in similar ways at different times suggests that the behavior is not random. The sequence of signal anomalies, magnetic field variations, and transmission phase shifts forms a profile that cannot be easily dismissed as coincidence. To date, no visual or spectroscopic evidence has confirmed the presence of any mass or field generating these effects. However, the alignment in waveform structure, rhythm, and timing across both missions points to a common external origin. If the same unknown factor is following or interacting with both probes, then it has remained undetected by all other instruments. Despite operating at the scale of interplanetary distances, it has neither disrupted the probes directly nor interfered with their mission objectives, but it has left measurable signatures that continue to defy current models. Who's watching? Voyager 2 is now traveling through a region of interstellar space where very little is known and even less has been directly measured. The signals it sends are weak, delayed by over 18 hours of light travel time. Yet within those limitations, the scientific community are still taking the data seriously. If such an object exists, it does not appear to emit visible light, infrared radiation, or known radio emissions outside the frequency bands used by Voyager. It does not respond to external commands or alter its behavior in a way that suggests real-time interaction. It has not interfered with Voyager's systems, its data stream, or its onboard equipment, but it has remained consistently close, as inferred from signal distortion and modeling of the spacecraft's flight path. There is currently no evidence that the object, signal, or presence represents a threat. If the presence is artificial, it has displayed only restraint. If it is natural, it is behaving in a way that appears organized but not hostile. If this object chose Voyager 2, that would mean this object knows we exist and how we communicate. It knows we search for patterns, and it is giving us one. All we have to do is figure it out. Thanks for watching. See you in the next one.